one more.
Thank you. I'll try to make it quick. So have you guys thought about using ChatGPT to do like test cases and verification instead of coding? Mainly because like storage devices like NVMe SSDs, typically you just read and write to them. It's a relatively simple interface, but we must make it reliable in terms of storage. So have you guys thought about different power cycling scenarios or different ways of possibly it could fail and how ChatGPT can help?
Yes, indeed. I think that the main advantage of, I would say, general AI, yes, because the ChatGPT is one of example, is that it's much easier to maintain code. As you mentioned, we are writing tests, yes, for instance, to increase this quality. When you have this automated tool, you add something extra, you don't need to create and recreate and add some additional information on the test, yes? So it's definitely a very good use for the chat if you need to frequently add something on the code, change it, modify it, yes? Because it's much easier to keep everything up to date. And I think that's very good usage of that. Yeah, thank you.
Start the presentation. Yeah, slideshow, perfect.
It's not displaying though.
It's there.
Okay. Thank you. Do we start it?
Okay, we are about 5 minutes to start. 4 minutes. 4 minutes now, right? Okay, but we can have fun. So.
Hello, good morning. I didn't hear anybody. Good morning. Good morning. Thank you. I hope you are having fun so far. So the previous topic was, I was hearing is ChatGPT, AI, pretty exciting, right? Well, this topic is probably not that exciting, but we'll try our best to make it exciting, okay? So the topic is CXL Memory Expansion Module error handling, solution implementation for better reliability. So this is how we have developed the CXL-based solution and what kind of fault handling capabilities that we investigated and then implemented in our design. Okay? My name is Anil Agrawal and Hiral. Both of us are from Meta, and we'll jointly present this topic. So what we'll do is we'll first briefly touch base on CXL Type 3 device. How many of you know about CXL? Great. And then we'll look into the fault domains when we have to use a Type 3 device in our machines. Okay? And then what kind of error coverage or fault handling solution that would be appropriate for managing those faults. So we'll talk about that, and a call to action. So if you look at Type 3 device on the right-hand side, so there are Type 1, Type 2, Type 3. So our focus is Type 3, is really to use for memory expansion. Okay? So memory capacity expansion, memory bandwidth expansion, and using some of the, having a flexibility to use alternate media types, DDR4, LPDDR, any kind of emerging technology. So it's a pretty exciting thing. But with every exciting thing, there are challenges. So what are different fault domains when we have to use a Type 3 device? So if you look at the Type 3 device in this block diagram on the right-hand side, the device is using CXL. CXL itself is a link, so the CXL link is a kind of, using link 2 times. So there could be link faults, right? And then there's a memory. So on the bottom side, we are showing the memory itself. And in this example, the DDR4, DDR5, could be any kind of memory. And there could be faults in memory also. So we need to manage those also, right? So there are 2 main fault domains, memory subsystem and the link itself. Now, let's focus on memory faults. This table is a little bit busy, so let me walk you through that. Okay? So on the first column is the different kind of faults that can occur in the memory subsystem itself. So first row is bit error, single bit error, and it's a transient error. Some bit got flipped. It's not really a physically bad device, but for some reason, high energy particle strike, the bit got flipped. What kind of techniques we have is ECC, error correction coding, and the demand scrub and petrol scrub. Those are techniques are used to manage those single bit transient errors. Now, what happens when that bit is actually a stuck bit? Well, ECC is still good, but we need to do something more than that, because now the bit is stuck and is always keep going, giving us an error, right? Error correction is happening, ECC, but there'll be error reported and overhead associated with error reporting. So we want to mitigate that by using OS soft page offline, or even PPR, which is post-package repair. We just will map out the whole row, okay? Even though it's a single bit stuck, but that's probably another option there. Then the next bigger fault is the row failure. And this row actually is within the DRAM device itself. If the whole row fails, then we need to even be more proactive and take an action on that. And PPR is really the most useful thing. And before that, we can do OS page offline also. But this is a little bit overhead associated with that when there's a whole row failure. And we could also do chip kill, where the whole device we can map it out, which is opportunistic. We would not like to do it, but sometimes it may happen. And after that, the next thing is bank failure or the whole device failure. So chip kill concept is used. Chip kill is basically any device which has a permanent persistent failure, we can completely map out the device and still run the machine successfully. Okay? So that's a chip kill concept. And the next one, which is in bold, is when the fault domain is beyond one device, so multi-device. And these are the DRAM devices again. So when there is a fault where two devices are involved, that becomes an uncorrected error. So ECC will not help there. So we need to do something beyond that. So what we do is kind of poison the packet or poison the data and contain through the poison concept. We call uncorrected recoverable UCR type of handling. And there are techniques called MC recovery, OS hard page offline to manage such failure scenarios. And then command address bits, which are link kind of errors, control path, like marginality on the link itself. And the command address parity retry concepts are used to manage those faults. And the last one, which is something we see quite a bit, is connector or the pin failures. Now, those are mostly detected during the like a training, the boot time itself, and we'll map out the DIM. The whole DIM or the whole channel will be mapped out. So that's how we kind of mitigate those faults also. So overall, there is a pretty robust fault handling mechanism that we can build, and we have built actually and can be deployed to manage the memory faults. The reason I put them into bold, the UCR uncorrected recoverable, because this is one of the very complex flow of complex solution to manage these faults. So actually, I'm going to give you an example and walk you through how we can handle these uncorrected recoverable events. Okay? So right-hand side block diagram. On the bottom is a CXL device, and in the middle is the CPU, the host. And then OS, there's a CXL mailbox driver. And at the top, there is a user space, all the utilities to report the errors and manage these faults. This is a very typical, very simplified view of a CXL Type 3 device-based system. So let's start with step one. Let's say I've written code, and I'm trying to fetch the data, the move command. Right? Now, that request will come all the way to the CXL device, because the data actually is in the memory, which is behind the CXL device. Step two, when the device is fetching the data, there's an uncorrected error, multi-device failure. Now, what's going to happen is the device is going to, first of all, make sure that the poison is contained, because it's going to set the poison bit as the data is being delivered to the host. So step three, the device return data with poison bit, okay? And the command that is CXL package defined .mem S2M, which is slave to master concept. And then host CPU will detect the poison, that packet with the poison bit. And this is where the host is going to, once it detects it, it's going to trigger a machine check exception, MCER. And then the handler will go through the whole recovery flow to make sure that data is never consumed. So the move command will never complete, right? Because it's an uncorrected error. And the recovery flow will then either first map out the bad page and then retry that transaction at the application level, or the application will get killed. The application that was actually requesting data fetch. Right? So that way we make sure that the system is contained, a system is still data integrity is maintained, and the data is never consumed without completely crashing the machine. Right? So that's the concept here. Now, from an error reporting point of view, there are 2 points of error reporting. One is point of detection. So the device itself, because device is the one that detected the error, is going to log the error in the event log handler. It's called event record in the device itself. And then the user space can do a polling to the mailbox to get that event log. And that event log will have a lot more details about where exactly the uncorrected error was detected, and the address and all the information about that. At the point of consumption in the host itself, when the recovery event happens, there again there will be reporting. And that time we'll say, hey, I got the poison, this is the address, and do something with that. So that's how the reporting will happen at that point of detection. Now, in the event log itself, what kind of information we have and how we can use that to pinpoint the actual DIM where the uncorrected error was detected. Because ultimately the end result or the end goal here is to find the DIM where the fault was detected. DIM is the FRU here, field replaceable unit. And we want to make sure that we replace the DIM if the error is repeatable. Right? That's the whole idea. So I'm going to hand over to Hiral, who's going to talk about the event log, how we use that to find out which memory or DIM where the fault was detected. And since Hiral did the most of the actual work, so I'll now hand over to Hiral for that.
So as Anil mentioned, here what we are representing is an example of an event record. So if you take a look at the CXL spec, it has very well defined the event record, but there are still some informations which were missing, especially how do you identify the FRU where exactly the event had occurred. So we worked with the CXL consortium to basically define the component identifier where exactly the device or the error event had occurred, so we can represent the event record correctly and take an appropriate actions on top of it. So here is an example of the event record. The important fields are basically marked in the bold. Very important piece is where exactly which physical address at the device level. This is the DPA, it's a device physical address where the event had occurred. How do we use this? It can be used, as Anil mentioned, you can basically do a translation at the host side from device DPA to system physical address and take an action on doing a page offline. So that could be your corrective action on the device or the specific address where exactly the event had occurred. The type of the memory event, whether it was S2R, whether it was M2S, depending on in which direction the event had occurred for the read or writes, transaction type, and the validity flag. Validity flag is where we basically worked with the CXL consortium to extend the validity flags to give us a flexibility to define any vendor-specific component identification. So the last one, the component identifier, here is an example like how exactly the vendor-specific component identifier can look like. So in this example, the first byte is representing what kind of event it was, whether it was a media event, it was a DRAM event. So here, the first byte represents the DRAM event. And the second byte we are using here to represent the DIM still screen. So in this case, you see 42, which is an ASCII value for the B. So we are representing that on the DIM B is where exactly the error had occurred. So this information we can use in our fleet to at a scale identify what is the device which is basically seeing the errors and can take corrective actions on top of it. So this is the summary for the memory device errors. So there are correctable errors. For correctable errors, we are recommending to use the OS first as the reporting mechanism. The CXL gives us a way to configure the MSI interrupts for the type of events. Either you can configure the interrupts for different types of the event severity and let the driver interrupt handler take an action on it. Or you can have an user space utility which is periodically doing a polling and looking for the event records and figuring out what kind of event had occurred and what is the next steps to take. Then the next is the device uncorrectable recoverable error at both the detection point and the consumption point. The detection point, we are recommending to use the OS first, where basically the error reporting can occur, and you can use the user space utility for polling mechanism, or you can have an MSI interrupts configured and let the kernel handle it. From the consumption point of view, we are recommending to use a platform-specific error reporting and error handling mechanism. When we say platform-specific, it is basically CPU-specific. So AMD can have its own implementation for the platform-specific error handling. Similarly, Intel. Now let's talk about the another fault domain that Anil described in the beginning of the slide. So far we talked about the memory. Now we'll talk about the CXL link fault domain. So this slide, the picture is quite busy, but what we are trying to represent here is, even though the CXL device or CXL link uses the PCI schematics from the 5-layer standpoint, it uses the same 8-bit, 10-bit, or 128-bit, 130-bit encoding mechanism at the 5-layer, but there are some details which is CXL specific, right? If you look at the CXL, it is a multiplexing of 3 protocols: CXL.io, CXL.mem, and CXL.cache. Because we are talking about type 3 devices, we'll only focus on CXL.io and CXL.mem protocols here. So at a data link layer and the transaction layer, they do the multiplexing of CXL.io and CXL.mem protocol, which basically gets multiplexed at the flex layer, and then 5-layer uses the same PCI schematics from the physical schematic standpoint or protocol standpoint. So here, in middle, we are representing CXL.io fleet and CXL.mem fleet. Basically, the CXL has defined a fleet concept to provide us the lower latency for the CXL transactions. The fleet are 68-byte fleet, whether it's CXL.io or CXL.mem. If we take a look at the CXL.io, it basically follows the same PCI like a packet concept. Here it is a fleet. So there is an sequence number, there is header, data, ECRC, LCRC, and the framing is same as the physical 5-layer framing. From the fault domain standpoint, at the data link layer, you can use the sequence number, which provides you the data integrity. And at the transaction layer, there is a 32-bit LCRC, which can be used to identify the faults. In case of a CXL.mem packet, which is again 68-byte flit, which consists of 16 bytes of chunk, there is a concept of a CRC, which is a 16-bit, 2 bytes of CRC, which can be used to identify the faults. And there is a poison bit as part of the header, which can also be used to identify the poison. Now let's take a look at the link fault coverage. So the first row identifies the bit error. So these bit errors, if you take a look at the PCI spec, they are very well defined. The link coverage for it, basically the fault coverage for the bit errors, they are correctable errors. You can use link CRC or retries, link retraining, or recovery mechanisms to basically correct this error and for the error reporting. The next one is an uncorrectable non-fatal and fatal errors. These are basically poison TLPs or malformed TLPs. These can be identified as part of a poison, which can be contained as part of a poison bit for both CXL.io and CXL.mem. And error reporting is also covered very well as part of the spec. The another concept is an eDPC. This also comes from the PCI, but currently the spec does not very well define how to use eDPC for CXL.io and CXL.mem. So we are working with consortium to identify how can we isolate the link level errors for CXL.io and CXL.mem and contain it into a specific link level. And the last one is a device internal error. The spec has defined a viral. So we use this viral mechanism to identify the device level internal fatal errors. This is basically mainly used for CXL.mem. So the host on the CPU side, it can be handled, the viral handling can be done at the platform level. And on the device side, the viral handling can be done at the firmware level from the device point of view. So here is the link error reporting summary. For all the link level correctable errors, uncorrectable errors, and fatal errors, we are recommending to use a platform first mechanism for error reporting mode. And here, because the CXL follows the PCI schematic, it basically uses the error messages, which is for correctable error, it is error correctable, error uncorrectable NF, error fatal. In case of a fatal error. So it uses exactly the same PCI AER mechanism to report the error. The handling of the error is platform specific. And it can be, the platform can configure an SMI interrupt, and there can be an SMM handler which takes care of each event and how does it handled and reported as part of a machine check. Now, call to action. As I mentioned, the CXL spec is still moving, and there are a lot of gaps as part of a spec, a lot of gaps as part of a driver developed, as part of a CXL PCI driver development. So you're working with the community to basically have a robust implementation, have a design discussions, and code development and review process for CXL RAS. So if you are interested, please join us for the Linux CXL group. As part of OCP, there is a sub-project called OCP Hardware Fault Management. This is the project is where we are defining the robust mechanism to identify the CXL faults and how to handle it. And lastly, if you have any questions, feel free to reach out to us, both Anil and myself. These are our email addresses. I think we have probably a minute, so.
Very well done. Thank you very much. You just saw another magic happening here. Hiral and Anil packed many, many, many years of experience into 15 minutes. Thank you.